Okay, this is a shorter unit, so the actually last thing that we have to discuss is something called L'Hopital's rule. And this is something that actually is considered by many the icon of calculus. I see that many Calc BC shirts have L'Hopital on it. People use it as like a joke. So we're going to talk about L'Hopital's rule. Now, let me just get the proper spelling of this so that later if you see the word you're not super confused. And this is right over here. L'Hopital's rule. Looks like that. Basically, this is going back, I actually acknowledged L'Hopital's rule back in Unit 1 when talking about limits, and I said, we'll talk about this later. Now we're talking about it. L'Hopital's rule is a way of finding a limit of something when it seems almost impossible, and it's kind of like the last resort almost to getting your limit. And basically what this is it's an idea. I can show you the proof, but I'm just going to cut to the chase and say that if you have a limit that, I'll give you guys an example. The limit as x approaches 2 of, make sure I have this right, 8 cubed minus 3, or sorry, x cubed minus 8, I don't know why I'm talking so messed up, over x minus 2. Now, looking at this from the first time, you're probably thinking, well, let's plug the numbers in. If you plug in 2 for x cubed minus 8, you get 0. If you plug in 2 for 2 minus 2, you get 0. So you get 0 over 0. I think a couple units back, you would never have gotten a problem like this, but you probably at the time would have just said the limit does not exist. Well, actually, it's kind of scary to say that you're not done because of this new thing called L'Hopital's rule. And basically, if you have any limit that equals 0 over 0 or infinity over infinity, then you can use a special rule to be able to kind of see if there actually is a limit. So what you have to do is take the derivative of the top and the derivative of the bottom, and then keep it in the fraction and take the limit again. So, and now what we're going to do is limit as x approaches 2, write that again, and the derivative of the top part is 3x squared. And the derivative of the bottom part is 1. So you then, now you're not going to get an undefined thing. You just plug in 2 for squared, be 3 times 2 squared, which is 12. So now you know that with L'Hopital's rule, you can actually find some limits that you used to think did not exist. So just a quick recap, if you have a fractional limit where you end up getting 0 over 0 or infinity over infinity, then take the derivative of the top and the derivative of the bottom and put it into a new fraction, take it again, and you'll many times find that the limit actually does exist. It just wasn't as easy to see the first time. I'm just going to do a quick example of a limit that would equal infinity over infinity. Okay, so we're going to do the limit as x approaches infinity of 5x squared plus 4x plus 1 over 2x squared minus 3x. So you plug in infinity, you would get infinity squared plus all this stuff, infinity, over infinity squared minus infinity, which would be infinity squared, or infinity. You get infinity over infinity, so what are we going to do? We are going to take the derivative of this. And once again, when I say this, I want to stress, I don't mean take the derivative of this, because that's the quotient rule, and you don't ever want to do the quotient rule. You take the derivative of the top, and then put it in the top of a new limit. Take the derivative of the bottom, put it in the bottom of a new limit. So this would be 10x plus 4 over 4x minus 3. Now, if you plug in infinity, you're going to use the leading coefficients and get 10 over 4 or 5 over 2.